Welcome to this session. In this session, we will talk about situations where we can use linear models. To do so, we first discuss the key assumptions that must hold true for linear models. Then, second, we will learn about how to validate linear models to estimate how well they actually fit the pattern in the data. To do so, we will use the example of professional soccer players and the relation of weight and height. So let's start. To describe data like the weight and height you see in this chart, a simple line is a popular way to do so. It describes the pattern in a dense and intuitive way. However, we can only use a line when two key assumptions hold true. The pattern should be linear and the variable we want to describe should be continuous. In this case, it's weight. So we have to check both assumptions. Let's discuss continuous variables first. Examples of continuous variables are height, blood pressure, or the cholesterol level in the blood. With a variable containing information of weight in unit of kilogram, this is obvious. In this case, we describe the variable weight in kilogram, and it is obviously a continuous variable, so we can draw a line. The line you see here is a result of this linear equation. The result is denoted with y hat. It is the estimated value, the estimated y value, that lie on the line. In this context, we say y depends on the linear model, and thus we call the y variable the dependent variable. And sometimes you will also hear someone call it outcome. So consequently, the dependent variable, the variable we want to describe, is shown on the y-axis. The information we use to describe weight in the linear equation, in this case, this is the height information represented as uppercase X, belongs on the right side of the equation. This X variable, that's the independent variable of the model, and sometimes you will hear someone call it the predictor. In this case, the independent variable is continuous, just like the y variable. But unlike the y variable, it can also be categorical. So we could have used groups to describe height. So for example, short players, medium-sized players, and tall players. But if we have continuous information at our disposal, we tend to use it because it generally contains more detailed information. To sum it up, in this case, the y variable is continuous and we can use a line. But does the line actually represent the pattern in the data? It will do so if the trend in the data is approximately linear. So is it? Full disclosure, because you surely already guessed. Of course, the relationship between height and weight is linear. X and Y increase hand in hand. But what would a nonlinear relationship look like? Here you see a nonlinear pattern. First, we see that X and Y increase together. Then, this trend turns when X approaches the value of 30, and then with increasing X value, Y actually decreases. As you see, a line does not reflect this pattern, and thus a linear model is not a good description of what's going on. As a quick side note, we can reflect the pattern using something called a polynomial regression model, which you see here. The polynomial model is an extension of the linear model. Statisticians call those extensions generalized linear models. But in this session, we will focus on simple linear models. So how do we check if the trend in the data is actually linear? A common approach is to look at the errors of the model, the residuals. This plot contains the residuals. The residuals are the differences between an actual observed data point and the estimated y value on the line. Just as a reminder, sometimes we also call the residuals the prediction error. In this chart, the red vertical bars represent the residual. Now the trick is to look at the distribution of the residuals. To do so, we could use a histogram, a common type of chart to visualize the distribution of a variable. In this case, the distribution of the residuals. Here is the histogram of the residuals. When we use a linear model to describe the pattern, then, and this is key, we expect the errors to be approximately normal distributed. Here you see a perfect normal distribution. So we expect the histogram to be approximately bell-shaped. Furthermore, the errors should be centered around 0. Both are true in this example. So why do we check for normality? Well, if the errors are not normally distributed, we suspect some kind of systemic bias, a pattern we miss with a linear model. When the residuals follow a normal distribution, we expect no systematic bias. We consider the residuals just as random noise. And here just another quick side note again. Another way to check the errors, instead of using a histogram, is to use a so-called QQ plot, which you see in the bottom right. Here we plot the quantiles of the residuals against the expected quantiles under a normal distribution. The point here is to check if the residuals lie on a diagonal line, like in this plot. Then, or in this case, we can conclude that the errors are normally distributed. So we visually check the assumption if the errors are normally distributed. First with a histogram and then with a QQ plot, because it's easy to spot if the data points are actually on the diagonal line. So we assume that the relationship we try to model, so the relationship between weight and height, is actually linear. So in this example, we learned about two key assumptions of a linear model. The independent variable is continuous and the errors are normally distributed. There are other assumptions we have to consider for a linear model, but in this video we discussed the two key assumptions that must be met to describe the data with a simple line.